Hello everyone, I'm Vidya. I will be one of your TAs for this course, and I will be taking 5 to 6 tutorial hours on HDLs and FPGAs. So today's tutorial will be on HDL introduction. We'll know what an HDL is, how we make an HDL design, why are they used, what are their advantages and all. So let's start. So before we define what an HDL is, I would like to discuss how we build a digital system. So these are the steps, overall steps that is involved in building a digital system. First of all, we have a problem statement. So for example, we want to switch on a light if someone rings the doorbell. That's one of the problem statement. And the other statement other problems would be like we have to do some computation of two numbers and get a output. Like we do some operation on two numbers and we get an output. So that is one problem statement. So like this, we have different kinds of problem statements. So we convert the problem statement into lab or project specification. So problem statements convert into project specification. So once we document the problem into a specification, we move on to describe the behavior of the system. So we go on to the behavioral description of the system. So in the behavioral description, we have we define the operations, functions, processes, etc. that is required to convert the inputs of the specification into the outputs. So that's what is done in behavioral specification. We generally design algorithms, we put the functional operations etc. in flowcharts and RTL description. We'll come to that later, what is an RTL and all. So the problem statement is converted into a behavioral description, and then once we have the algorithm, the flowchart, the state descriptions and all, we convert it into a Boolean logic and state. This is by this what I mean is the behavioral specification is converted into set of equations or a circuit schematic, so that we can put it onto the real physical device, an electronic device. So we have in Boolean logic and state, we have logic equations and we have a circuit schematic. And once we have the logic equations and the schematic, we convert it into a particular hardware. For example, AND or etc. So the equations will be converted into a physical entity. So this is an overall view of how a digital system is built. So in earlier days, we used to have, the designers used to build hardware by using paper and pen. So they had to write the equations, they had to solve Carnot map, K map, they have to solve everything, and they have to like manually do everything. So as the complexity of the design increased, people wanted a more automatic way of doing things. So when the complexity increased, we moved on to replacing the Boolean logic and state as an HDL description. So this is where our HDL comes into picture actually. So HDL description is basically like helping us to overcome the complexity of the designs that we are facing nowadays. So the main motivation behind HDL is like how I have told, the specification. We have a problem statement, we convert it into a project specification, and the specification has some goals. So a specification maps into some goals and then methodology using which we design a system. So there are two things. In goals, we design, we define how the system should be, what is the cost that is required to build the system, what are the power requirements, what are the latencies, functionalities, etc. That uniquely define the system, and then we can go back to that goals and check if that are met or not in the end. And second thing is the design methodology. So there are two types of design methodology: top down design and bottom up design methodology. So in a digital system, for example, if you consider a very big system, if you take a smartphone for example, we have a lot of functionalities that are integrated into it. So in a top-down approach, we break it down into smaller modules and interfaces, and then we approach each modules and interfaces individually. So that is a top-down approach. And in the bottom-up approach, what we do is we first do the smaller modules first and then integrate it up to the higher level. So generally we follow top-down approach because we usually start with the bigger problem and then break it down into a smaller problem. So for example, that I have mentioned in the slide, that we have ISA, that is instruction set architecture of a processor. So if we have a well-defined ISA, it will be there for a longer time, that we can use it for a longer time without actually facing any problem with the definition of the ISA. So that's the example of a very good specification. So this specification, actually what it helps us to do is to model a functionality. So we say that it is a behavioral model, and this behavioral model is used as an executable functional specification. So we have problem statement, we have project specification, and the specification is converted into a model using an which serves as an executable functional specification. So what hardware description language or HDLs mean is that we don't have to know exactly what the hardware is. We want to have we have tool chain or something through which we can design the hardware without actually knowing what exactly the hardware is. So we want to know what the hardware functions, like we want to know what the mobile does. We want to make calls, we have to receive calls, we want to send messages, but we don't want to know how exactly that is done. So HDL is a way to help us do that and map a functionality to a hardware. So if the mapping is, I'll come to it later what synthesis is. So basically we synthesize an implementation of a behavioral model. That is what hardware description language does. And there are, like in the current industry, there are 3 HDLs that are being defined, that are being used actually. So first is Verilog, second is VHDL, and third is system Verilog. So in our discussion, we'll mostly discuss Verilog and VHDL, and in the later tutorials, I'll take some of the Verilog basics and some advanced concepts of Verilog. So through Verilog, we'll try to learn how to write a Verilog code basically to build a digital system. So since now we know what an HDL is, we'll look into what are the advantages that HDL gives us to build a digital system. First is levels of abstraction. So we abstracted the levels, like we don't have to know exactly what the hardware has to do. So we have abstracted out the exact implementation from the behavior. So we just have to know what the hardware does. That is that's the most important advantage of HDL, because nowadays we have so much complex systems that not everything can be like decided at the first design phase. So this helps a lot in that. And second thing is functional simulation. Functional simulation is basically we are testing the functionality of the design, whether whatever we are thinking what the design does, it's actually being the design does that. So that's what functional simulation does. So it verifies whether the functionality of the system is right. So we can do functional simulation using HDL very early, like before the hardware actually comes, before it is built, we can do the simulation of the design. So that's how it helps in functional simulation. Third thing is the HDL code directly gets converted into gates using some tools that I'll discuss later. So we don't have to like draw the schematic and then convert it into hardware gates, and then like it takes time, and we can fix any errors easily if we are using HDLs. So if we are doing it by hand and by paper, it's very difficult. And there's something called technology specific netlist. This also I'll come to later. Basically an HDL code gets converted into gates using a process called synthesis, and generally we have standard tools to do that. And fourth thing is we can like if for example we have a design, it can be implemented in different ways. So using HDL we can do that implementation in different ways in a very small time. So we can test, we can design the implementation, and we can test the implementation. So that is another advantage of HDLs. Last thing is design reuse. That if you have heard, I don't know, we have IP blocks, so intellectual property blocks, so which are being reused again and again for different purposes. Like if a company has designed an IP, it can be used in some other company if that the source company allows it to be used. So design is reusable and it is portable across different technologies if we are using HDL. So these are the main advantages of HDL. So next we will discuss the two main HDLs that there is currently, VHDL and Verilog. So VHDL was initially developed for creating ASIC synthesis. ASIC is an application specific integrated circuit. So for synthesis of ASIC systems, VHDL was used, and it was developed by US Defense Department. And if you see Verilog was used for gate level simulation of the gates basically, and it was developed by a company called Gateway Design Automation, and that was acquired by Cadence. So and VHDL is very verbose kind of language, and Verilog is a C-like language. So it is very easy to understand Verilog, and it's comparatively harder to understand VHDL. VHDL has some package management structure, and it supports package management for larger design, but Verilog doesn't have such extensions for larger designs. And if you see the way the code is written in VHDL and Verilog, in VHDL we have entities, and the entities will have architectures inside them, and architectures have configurations. So this is how a basic structure of a VHDL code looks like, and in Verilog we have only modules. So from this only you can see how different it is. Like VHDL has it is verbose. From this only you can understand how it is a very like richly typed language. So there's something called modeling. There are three different types of modeling: behavioral, structure, and logic. Both VHDL and Verilog support those. We'll study in detail what these are with respect to Verilog. And there's something called synthesizable subsets, which allows us to port the Verilog description into hardware. So Verilog and VHDL can also be used for simulation purposes, which doesn't map into a hardware. So there are specific synthesizable subsets that can be mapped to a hardware. Like the last thing is what I told, like VHDL is hard to learn and use, and Verilog is easy to learn because it's very similar to C. So these are the main difference between VHDL and Verilog. So in our tutorial sessions we'll be mainly dealing with Verilog. I've been talking about synthesis a lot in the previous slides, so we'll see what a synthesis is. We talked about how HDL serves as an executable functional specification, which defines a digital system using a design methodology, where the designs are divided into modules and interfaces. So the executable functional specification documents the behavior of modules and interfaces, and it can be tested and refined. So that is what executable functional specification is. So HDL is the first step to automate all the process of digital design. So this executable functional specification, we can take it as HDL description, which is given to a logic synthesis tool, and we get a gate level netlist. So what I mean by logic synthesis is we have an HDL description of the system, we map it onto a hardware on like AND gate, OR gate, or counters, or some higher level ALUs example like that. So to get a netlist, we feed the HDL description and feed target libraries into the tool, which has the basic primitive logic gates and digital constructs basically, and which is technology specific. So we give the HDL description and we give the target library to the tool, and the tool synthesizes a netlist. Netlist is generally a file in the format EDIF, which is electronic data interface format, data interchange format. So that is technology independent. Like any vendor can take a netlist and they can use it to do further processing of the system. I'll come to this later. So what we have understood is HDL description maps to a gate level netlist using a target library, and this is iterated over and over and again for a higher speed and lesser area perspective. So we want the system to work very fast and we want it to use smallest area possible. So we try to like optimize the design for the same. So now the whole process is called functional design, and it is a part of front end design. And once we get the netlist, we have to map that netlist onto the board, onto a physical system. The physical system can be FPGA or an ASIC. So the gate level netlist, it's placed and routed to an FPGA, to a particular device. So how we do that is, for example, if we are building a if we are making a big building, we have floor plans architecturally. So like that, once we have the small blocks that have to be made for the digital system, we make a floor plan of the whole system, and we place particular modules and particular places on the hardware, which is basically our space where we will put the design. So we place the design and then we connect different modules to get the whole system. So this same thing, we again optimize the thing, we place it here and then, and we check which is the optimized path which will give us the highest speed, less area, less power. All these things are done. So now we have a design on the on the FPGA. So this process is called physical design or backend design. So this is how we convert HDL description into an FPGA or ASIC. This is how we build. So in this tutorial, we'll mostly consider FPGAs, and I'll be teaching how to design a system or how to develop a small basic embedded system on FPGA. Okay, so the HDL implementation cycle is in overall like this. So we talked about product specification, we talked about behavioral description, etc. So that is what is called design entry, which we specify using the Verilog code. And then we check the functionality of the design by doing functional simulation. So we check if the computation is being performed properly or not. So that's a functional simulation, and from Verilog we do synthesis of the Verilog code and we get a gate level netlist. So in that level also, after the synthesis, we do gate level simulation. We check if after the logic has been ported into a netlist form, whether still the functionality is same or not. So we do gate level simulation. Once we are done with the synthesis and the gate level simulation, we implement the design, map it, place it, and route it on the hardware. So this is the basic HDL design flow, and hope you understood where Verilog comes into picture and how we'll use Verilog to build a digital system or an embedded system as a whole. So that's all for today, and you can have the reference of slide. If you want to know more about it, you can refer to these links. I'll share the PPTs. Thank you.